where I left off last time, and I'm going to go up one notch here. Where I left off last time is talking about how rainbows work. And so far it didn't look like rainbows at all. I was just talking about seemingly random things associated with sunlight's passage through materials. So let me just try I'll remind you what we've discussed. I'm going to back that back down. And then get on through rainbows and on through the rest of sunlight issues. So when light stops traveling through empty space, when light enters the Earth's atmosphere, it starts to interact with the particles that make up the Earth's atmosphere. It polarizes them, and that can cause, among other things, Rayleigh scattering, where it manages to sort of be absorbed and re-emitted in new directions. That's the blue of the sky and the red at sunset. When light continues on through the atmosphere, as the atmosphere gets thicker and denser, the light slows down. So that was one of the first observations. It's caused by the polarization effect, that the light the atoms, the particles of matter, sort of play with the light. They polarize in response to it, and they delay the light's travel. They cause it to lag slightly behind what it would do in empty space. And that slowing down process it depends on the material, and the material is then characterized by what's called an index of refraction, the factor by which the light slows down. So it's always a number 1 or greater. Empty space has an index of refraction of 1, and once you start putting things in the space, the index of refraction gets a little larger or larger as the material is more able to polarize and more able to slow down the passage of light. So far, so good? Questions? Okay, that slowing down effect, the index of refraction, is a little oversimplified because the different colors of light, which is to say the different frequencies. I'll talk a little bit when we get to discharge lamps later, hopefully later today, how we perceive light and what the relationship between frequency and color. But just in general, we perceive the highest frequencies of visible light as blue color. That's how our eyes and our brains respond to it. And the lowest frequencies of visible light we perceive as red light, and then the whole rainbow in between. So the rainbow spectrum that you're used to seeing in a rainbow is actually swoops across in frequency from the violet blue end being the high frequencies to the red end being the low frequencies. Those different frequencies of light actually travel at slightly different speeds in materials. There's always some difference. In some materials, there's an extensive difference. And that difference in the speed with which light travels through material, depending on frequency, is known as dispersion, just to give it a name. And in general, the blue-violet end of the spectrum travels slower than the red end of the spectrum. There are exceptions, and then it's called anomalous dispersion. But dispersion is pretty universally, the blues go slower. All right. That's one feature you need to know in order to understand how rainbows work. Light slows down, say in water, and it slows down more at the violet end than it does at the red end. That is true of water. Okay, the other two things you need to know in order to see how a rainbow works is that when light goes through an interface, the surface between two different materials, and the character of how it polarizes the material suddenly changes. The light undergoes both reflection and refraction, or partial reflection, reflection and refraction, just leave it at that. The most obvious way in which the polarization change is manifest is in a change of speed. So when light encounters a surface and changes speed in going into the next material, some of it will reflect, some of the light wave will reflect, and the light wave that continues on may not continue on in the same direction that it started in. So the reflection, obviously called reflection. Refraction is that bending of the path of the wave once it enters the second interface. All right? I showed it to you last time, these partial reflections. The bigger the change in speed at that surface, the more reflection you get. More reflection you get, and the stronger the bending process becomes. I told you last time the bending, as light slows down, it bends toward the perpendicular to the surface. I hope you have a sense for what I meant by perpendicular surface. If this were transparent, which it isn't, of course, and light hits it, if light hits it straight on, there's no refraction. It's coming in at a perfectly perpendicular angle. It continues on at a perfectly perpendicular angle. But if it comes in at less than perpendicular, somewhere down like this, if it slows down, it will bend toward the perpendicular, and the perpendicular is the line that is exactly perpendicular to the interface. So it comes in at an angle like this, it'll bend, as it slows down, it'll leave heading more towards this perpendicular direction. And it does the reverse if it speeds up. And those changes will become more important when we encounter things like how lenses work, or how fiber optics work, how fiber optics carry light vast distances trapped inside a piece of glass. Okay, so when light enters a raindrop, and just to set the stage properly here, raindrops when they're falling are not tear-shaped, they're spheres. They don't have that little neck popping up out of them. The water droplet has what's known as surface tension. There's energy stored in the end of the surface where it leaves the drop and it encounters air. There is potential energy in that stretched surface, and it tries to get as small as possible. And that pulls the drop into a shape where it minimizes its surface while still having all the water there. And the shape that minimizes surface is a sphere. Any other shape has excess surface. So the drop pulls into a sphere. So the sunlight encounters raindrops. It's entering spherical objects. And it undergoes refraction at the surface, and reflection at the surface, and dispersion occurs inside the drop itself. That is, the different speeds, different colors of light travel at different speeds. That refraction process where the light enters so suppose the light enters a piece of glass, or a piece of water, just to be consistent here. When light enters water, so this is the top of, and it undergoes refraction to travel at a different angle after entering the surface, if the material it enters, namely water, has significant dispersion, that is, it really handles reds and purples differently, violets differently, then it will bend them differently too. They'll refract differently. So refraction is affected by the difference in speeds for the different colors. And the result is that the red light bends less than the violet light when light goes from air to raindrop, because the red light doesn't slow down as much, so it doesn't bend as much. The violet light slows down a lot, it bends more. And the two colors get separated. They may have been traveling the same path from the sun. A little wave of violet light and a little wave of red light traveled all the way from the sun, hit the raindrop at the same exact spot, and they no longer travel together. They've been going 93 million miles side by side, and suddenly, oh, they're going in different directions. And the raindrop then takes advantage of that, bounces the light around a bit, and the two colors never get back together. They go off in different directions from the raindrop. Before I go too far along, let me just show you the effects of dispersion and refraction working together. And the classic way to do that is with a prism. So I'm going to blank this guy. Okay, I'm going to send light up. It would go to the ceiling. It's an overhead projector, but we're not using the projector part. The light would go to the ceiling, but instead it enters this triangular shaped prism. In cross section, it's a triangle. So the light enters here, the back of the triangle, and it bends sharply toward the perpendicular because it's slowing down. So it bends, heads through the middle of the prism, and then it leaves the prism and bends away from the perpendicular, like that, and then up to the screen. And it has to have the sound effects. But because the red light is less affected, it doesn't slow down as much, it just doesn't bend as much in either of the two occasions, on entry or exit. It bends less, and it ends up there at the top of our little rainbow. The violet light bends more sharply. So this light bulb, of course, it's an incandescent lamp, and as I said last time, incandescent lamps produce a black body spectrum, a thermal spectrum of a not hot enough surface. They're not as hot as the sun. They produce the reds pretty well, they produce the greens okay, and then when you get to the blues, they're pretty wimpy. So there's not a lot of blue to work with, and that's why the blue part at the bottom of our rainbow is so weak. If we replace this lamp with some of the modern light sources that have a lot of blue in them, it would have a better blue end of the spectrum. But the main point here is that the light waves of different frequencies that we're all traveling together have been dispersed, in effect, by the combination of dispersion itself, that the blue light travels slower, and refraction, that the light gets bent, and the bigger the change, the more you get bent. Questions or thoughts about any? Okay. So, get this guy back up. I'm back. All right. So then, how does a raindrop work? Or a rainbow work? So it's always a struggle to get the whole story clean. I'll give it my best shot. To see a rainbow, you will not see one at noon. You want the sun low in the sky behind you. And you want the light from the sun to come at a relatively shallow angle across the fields behind you, whatever, and encounter raindrops in front of you. So you're facing away from the sun towards rain, toward all these droplets. And all those droplets have light come in from the sun. The light enters them, bounces off the back surface of the raindrop, and comes back towards you and comes to your eye. And in doing that, it does sort of three interesting things on its way. So here's the light coming over your shoulder. There's you staring off to the right. Light comes in over your shoulder. It enters the top of the raindrop. There's a certain region here. And people have studied raindrops, trying to figure out exactly how does a rainbow form. And there is more than one rainbow that can form. You may have seen double rainbows. There are, I've seen them on occasion. There is more than one path through the raindrop that creates interesting colors to see. This, however, is the dominant one after some much study by people who really cared about, not the point I wanted to use. So light comes in toward the top of the raindrop, and as it enters, most of it enters, a little bit of it reflects, and we're not going to worry about that. That light goes off to somebody up here in the clouds. So most of the light enters, and I should tell you how much is reflected. It's in the order of 3 or 4% per surface when you go from air to typical transparent materials. The reflection of a window is about 4% in the intensity, which is measured in terms of power per surface. So about 4% of the power goes off and it never enters the raindrop. The remaining 90 some odd percent go into the raindrop, and incidentally, they don't go the same path because there was refraction here. So the violet end of the spectrum and the red end of the spectrum were already getting a little separated. Those light waves continue, and they encounter the back of the raindrop, as far as they ever get away from your eye. And most of the light goes right out the back of the raindrop and is lost and is boring and nobody ever sees it. Well, maybe somebody sees it, but it's not interesting. So about 4% reflect off that other surface. This is why rainbows are weak. They're not super bright. So the light bounces off that surface. The stuff that leaves, we don't care about anymore, but the stuff that reflects, that 4%, heads back toward the front of the raindrop. And again, red and violet are traveling different paths. And finally, most of that light exits the raindrop, but it undergoes refraction again on its way out. And the refraction is, as before, it's color dependent, which way the light ends up going. And when all is said and done, the full mixture of light that came along, sunlight, that hit this particular raindrop comes out, fanned out in space in different colors. The red is on the violet is on top. So it's like what I did over here, except reversed. The violet light is the top of this of this raindrop's spray of light. And of course, there are many other raindrops at all altitudes. And so when you look out at these droplets, you see one color of light coming from each band of raindrops. The raindrops at a certain altitude will send light toward you that is, say, in this case, red. Up there, that's only the red light that's coming at you, because the violet light went over your head. The violet light from that band of raindrops went over your head. The lower raindrops create their own fan of color. And the purple raindrops are the ones that reach your eyes. The red raindrops go below your feet. So what you're doing, you're looking out there at the rainbow, and it's actually an arc, because really this whole thing has a rotational. It's not about the horizontal surface of the land and stuff. It's about the angle away from the straight line from the sun through you, through your eye. There's an arc shape to that angle. I won't go into it any more than that. But you're seeing pieces of the light from each arc. You're seeing one color per arc. It's okay, good enough? Basic idea. So it all depends on, what's responsible for this is the fact that sunlight contains this broad mixture of frequencies. They get separated as they enter and as they exit the raindrop, and they bounce off the back. So you got refraction, reflection working together along with dispersion to spread out the light and give you the rainbow. All right, that's the story of rainbows. Any questions? All right. So that is one way to separate the colors of light, and that is one that dates back to Newton knew about these sorts of things. The light was a wave. Light was very simple. He would understand all those features. I'm going to leave that question out. This separation of colors, they would have seen, would they have understood it? I guess they might have. Okay, I'll do this anyway and not worry about whether, how long back people understood this phenomena. But you've looked at soap films, like just soap bubbles, blow a soap bubble and you watch. It's got colors in its surface. You see light come off of it with colors associated, or a spill of oil on water. So when the puddles form on a rainy day and various drips of oil or whatever that are there, you see this beautiful colored pattern on the drops. Where does that come from? And it comes from a different way of separating the colors of light. It has nothing to do with refraction. It has to do with interference. And the idea here in the soap film, if we have that soap film horizontal in this case, so this gray picture I've got here, this gray rectangle, is a slice through a piece of soap, it's a soap film. Otherwise, in air, it could just as easily be oil sitting on a layer of water. It's all the same phenomena. So when sunlight encounters this one special thin layer of watery stuff, it slows down. The usual rules apply, and part of it reflects. So the wave that was coming in here is now divided into two pieces, two what are called partial waves, just to give them a name, and they are perfectly similar except in intensity. One of them is weaker than the other. It's just not as strong. Its electric and magnetic fields are weaker. But otherwise, they are exactly the same. And so this wave comes in, splits into two halves. The one that enters bends a bit by refraction. Of course, it goes more perpendicular to more along the perpendicular, bends toward the perpendicular. So down it goes, and about 4% come off the top surface. Well, that portion that went into the film soon encounters the back surface. And again, part of it reflects, about 4%. Up it comes. The remaining part just drills through and goes off and is lost. You don't care about this light that continues on. But you've got about a 4% reflection off the top surface of the film and about a 4% reflection off the bottom surface. And the light from the bottom surface eventually reaches the top surface, and most of it goes through. And there's a second reflection, but second reflection, but we can ignore that one too. The two that we care about, that will be most important in this story, are the reflection from the top surface and the bottom surface. And the reflection from the bottom surface has a longer path to travel. It is a perfect copy, it's a piece, it's a partial wave of the original wave, and in that respect, it exactly resembles this top reflection, and it travels in the same direction as the top reflection. The two little pieces of wave, partial waves, are identical, traveling the same direction. The only difference is one of them is a little delayed. The one that went to the bottom is a little delayed relative to the other. So its wave crests, and again by wave crests, and you have to identify some feature in this electromagnetic wave. So we can imagine the moments in which the electric fields are strongest upward. So we'll call that a crest. So the two crests of these two partial waves, they're traveling, each wave has many crests. It's got some length to it. But the crests associated with the bottom reflection are delayed relative to the top reflection. You okay with that idea? And they go and they go and they go and they encounter your eye and they encounter your retina and you see them. Well, it's a little trickier than that, just seeing them, because if those two waves arrive such that their electric fields are in sync with each other perfectly, so they both have their crests at the same time, their troughs at the same time, back and forth, they're working together, the response of all the polarization effects in your eye and the intensity that your eye ultimately detects is strong. So you see bright. The wave is strong there. And that's known as constructive interference. And I should have talked about constructive interference back when I talked about how microwave ovens work, because it was on your problem set for Wednesday and I screwed up. I just left that on the table. So you get constructive interference, and you can get interference in general, but constructive interference anytime you've got an electromagnetic wave that you break into two pieces and then you recombine in such a way that the electric fields are the two pieces of pieces of the wave have electric fields that are in sync. What's called in phase is the real term for this. When they're phased together so that they both have a crest at the same time, trough at the same time, crested. Is that okay? On the other hand, if the wave's delayed, that bottom reflection is delayed a different amount, it arrives out of sync, or technically out of phase, with the other wave. The two of them fight each other. The electric fields are in opposite directions. They're essentially equally strong, pointing in opposite directions. They kill each other off. You see nothing. So this, what this eye up here is seeing is the two reflections working together. Because they are pieces of the same original wave, their synchronization is potentially perfect. The question is really how their phases are set. Are they in phase with each other or out of phase with each other? If they're in phase, you get constructive interference, you see bright, and it's bright. If they're out of phase, you see destructive interference, it's dim. And whether this eye sees constructive or destructive interference depends on the wavelength of the light, because this extra distance traveled by the wave is a fixed amount regardless of the wavelength of the light. But if just the right number of wavelengths fit into this extra distance, you can still have the two waves come back together and be in phase, because one of them will have simply just wasted a phase traveling through the soap. And it'll be a phase, it'll be one cycle behind, but it will otherwise be identical to the top reflection. On the other hand, if you change the color, which is to say you change the frequency of the light, and therefore its wavelength, the delay in here might be such that the two partial waves arrives your eye out of sync. So the long and short of it is, some colors go into the film, come out as the two reflections, and experience constructive interference. You see them as bright, and other colors go through and you see them as dark. Ask me questions if this is fuzzy. See, code of silence. I will show you this two-way. Well, you can see it live, and you can also see it on camera. Of course, modern era, you probably believe the camera more. Is it? Yes. What you are looking at right now is this ring here, can you see my hand? Oh, I can turn the light on and make it better. Okay, so there you are, okay? There's a ring there. We're just gonna do soap bubbles, but I'm not gonna blow them. I'm just gonna have the ring hold the bubble. So I'm gonna put the soap on. And you can look live or you can look on the screen. And what you're seeing there is the film is not of uniform thickness. Gravity makes it thicker at the bottom than at the top. And of course you get the swirls of fluid flow of all sorts of stuff. But where you're seeing pink, for example, that's a region in which the top reflection and bottom reflection the bottom reflection is delayed just the right amount so that pink, the reddish part of the spectrum associated with that, is experiencing constructive interference. Where it's green, you're seeing constructive interference for the green waves, and so on. It's with a little care, probably a lot of care actually, I can hope to get horizontal lines that stay horizontal for a while. Yeah, sort of horizontal. I'm not quite sure why. What have I done with the light? Yeah, well, it's good enough. Okay, so these are this is an interference effect. It comes completely from the wave nature of light, that it has this ability to have the wave be in sync, or more specifically, in phase or out of phase, and everything in between. Questions about this idea? Yeah, Genesis.
I understand that they have to move at the same time. Like, what path is interfering? Like what it says on the slide, I don't understand what path is interfering.
The two paths, I've drawn them as though they're separated from one another by this, some distance. They're not actually separated by much distance at all. In fact, they overlap. I'm pretending the wave here is infinitely narrow. It's not really. It's actually a whole spread out wave hitting the surface. The top is reflecting, the bottom goes further and then reflects, and they're traveling really on top of each other. If I don't oversimplify it as much as this drawing does. This is a cartoon version. In the real world, this top reflection is a broad thing. The wave is a broad thing. It's been traveling since the sun. It's actually it's spread out. And the same thing with the bottom reflection. The two waves literally overlap, and they are literally fighting each other or helping each other. It's ATR. Does that help? And you can see that one of them is delayed. Other questions? Thank you for asking a question. All right. Yeah, it's in trying to teach this stuff and you write the book, you look at all the other books, you look back at other people's descriptions. It's easy to just draw the sunlight as one single line and then the bounces and so on, and to just assume that everyone will understand what that means. And it's hard to remember all the ways in which people can take things too literally. So whenever you see drawings of the travel of light, for example, as a wave, you know that lines are an oversimplification. Waves have some width to them. They spread out. They have they're a surface more than they are a line. That's also oversimplified, but at least question the drawings. They're not always exact representations of the story. Yes, I will ask this one. Sunlight consists of countless independent light waves. What waves are interfering to produce the colors of a soap film? And they're really I give you two choices. Parts of the same wave or different light waves. That is, light waves that were created independently at the sun's surface. You okay with the question? How many of you think that it's parts of the same wave that are interfering? How about different waves? Okay, so it's about an even split. And this is another one of these things that gets wildly oversimplified when it's normally presented. It's actually parts of the same light wave that are interfering. The different light waves from the sun. So just make sure you understand what the story is here, because it has some importance, and it will be quite important when we get to something like a laser. The light waves that come from the sun are countless tiny little light waves that have no relationship with each other. They have different frequencies, they have different spatial characteristics, which way they're going to go and so on. They don't care about each other at all. And when you overlap them simultaneously on something that senses light like our eyes, they produce essentially no interference effect. Why? Because the electric fields, their two independent electric fields, are so messy relative to each other that the chances that they would work together for any length of time or at odds for any length of time is almost zero. It's very, very unlikely that they will interfere in any meaningful way. They're just unrelated things. So the interference that you're seeing with this here, of course, I'm not using the sun, but the light is the same idea. It's buckshot. It's lots of independent waves. And the interference is entirely one wave with pieces of itself. It's pieces of the same wave. So the interference effects are kind of wimpy because each wave can only interfere with itself, and all the other waves, it just ignores them. It's a little hard to bring that story home in a way that makes it impressive or interesting. So where this is going to go is when we get to start working with a laser has the amazing ability to produce a giant light wave. That is a light wave where it's just one wave. It's not buckshot, it's a single wave. Not all lasers produce a single wave, they can produce multiple, but it's a small number typically. And so this laser pointer, it's one wave coming out of there. And that wave, if you break it into two halves and you overlap it, you get tremendous constructive and destructive interference effects, because if the waves arrive on top of each other, electric fields pointing in the same direction, you get a huge constructive effect. If otherwise, you get huge destructive effect. I can show you this, actually. I was thinking, how do I show you this effect without blinding us? I'm shining a laser pointer, just one simple laser pointer, at the screen through a grating. And the grating blocks out, it's grill work, very small grill work, but it's blocking out parts of the wave and breaking the wave into a couple of partial waves. And those partial waves are heading towards the screen, and amazingly enough, they experienced destructive interference almost everywhere except at the 4 spots that you see on the screen. You see them? There's the original one. That's the straight path. But then there are other ones coming left to right. Those are the very special angles at which you get constructive interference. Everywhere else, you get destructive interference. And it's the whole wave interfering with itself. Or like big chunks of the whole wave. The point of this whole story then is that you get dramatic interference effects with lasers. All right, we'll get there. Last thing I want to talk about with sunlight and the world around us. So you can see where the rainbows come from and all the colors. And of course, the story of rainbows shows up in all kinds of cut glass things. So this is, and jewelry, diamonds. There was a question I just skipped over about diamonds. Just diamonds, the reason diamonds are so appealing visually, I mean, for whether or not they're valuable enough, who cares? But they're so appealing visually is because first off, they have a very high index of refraction. They really slow down light a lot, so therefore they have strong reflections at their surfaces and big bands in their refractions. Second, they have a lot of dispersion, so that violet light goes a lot slower in diamonds than it does than red light does. So the colors get separated very severely. So between those two effects, you get lots of sparkle out of a diamond, that being the reflections, and you get a lot of color separation, that being the colors that you see. To duplicate that, there are other synthetic gems that do that. So one of the cubic zirconia is the current favorite fake diamond. It also has big index of refraction, lots of dispersion. You get the same sparkle and colors. What else with this? Another thing of interest, most of the white that you see around you, white paint, I wouldn't say white clothes, we'll get to white clothes and stuff, but the white of white paint or the white of white paper, you know, what is that? It's little particles of something with a high index of refraction so that there's a lot of reflection off every surface. And so the light really bounces off, and by the time you get deep enough into the particles, all the light's been reflected back. And the particles that are in vogue now are titanium dioxide. So if you ever wonder what's titanium dioxide, you read it on a package. It shows up in everything. I think probably toothpaste has titanium dioxide in it to make it white. It's got a very high index of refraction. It's quite clear. There's a yellowish tinted version of the crystal, but titanium dioxide, it's got a very high index of refraction, so it really has a severe reflection off its front surface and off its back surface, and it just sends light off in all directions as a powder, and you end up with a nice white. So far, so good? Before titanium dioxide, what was the powder that they used? It had a high index of refraction, really takes light and bounces it off nicely. And I also hope that you understand that why you get white if you have this sort of crushed surface. The particles are big enough that they don't do Rayleigh scattering. They're big enough they do more sophisticated scattering, and you can think of it as off the surfaces, and it goes every which way, and that's whiteness. Is that okay with the origins of white? Before titanium dioxide, what was it? Lead carbonate. So the lead of lead paint, some of the lead of lead paint was associated with the colors, but most of it was the white. They used, bad choice. They used lead carbonate powder to give that nice bounce to the light. And the results are, we're still living with lead paint problems, and will be until who knows. Before lead carbonate, there was whitewash and Tom Sawyer. It was just lime. You put lime particles, and you got white. But because the index of refraction is not very high, you needed a lot of it to get a decent white. The beauty of titanium dioxide is because it's got such a huge index of refraction, the reflection off every surface is big. You don't need very much of it. All right, so that's my public service announcement. Avoid white paint on houses before about 1930. It's not for eating. All right, why do polarizing sunglasses reduce glare? So first of all, what's glare? Let me show you glare. And I can put this camera. There'll be a huge part of the videotape in which you're staring at an empty frame for a bubble. Okay. I cannot do two things at once. Okay, so this is glare, right? That surface of the table is just coated with, it used to be coated with a transparent plastic. It's been so scuffed up that it's pretty damaged, but there's a reflection clearly of this light off the table surface, despite the fact that the table surface is it's not metal, right? It's not a mirror the way you're used to. It's reflecting, well, because that plastic surface is transparent enough. The light is trying to enter a material in which it travels at a different speed, and so part of it reflects. You're seeing the partial reflection. And the partial reflection in this case is at a shallow angle. And the 4% that I mentioned before is for straight on, when you go straight into a glass or plastic or water, then you get about a 4%. This, because you're at a shallow angle, it's not 4%. It's more complicated than that. And it can be much higher than 4%. But it's still more complicated. And here's the reason it's complicated. It's because the light now, when it's coming along, suddenly polarization matters. And the polarization, how you describe polarization in this shallow angle bounce is a little messy. But let's make life simple and think of the light can either be sort of vertically polarized with its electric fields going up and down, even though it's a little tilted. The wave is heading down, so the electric field doesn't go full vertical. It goes up and to your right, and so on. That's vertically polarized. It's got optical physicists have more complicated way of referring to it, but we'll leave it at that. And then the other possibility is horizontally polarized. Electric field back and forth like this. Is that okay? Those two waves get a different result when they encounter that surface, that horizontal transparent surface. The one that is horizontally polarized, electric field like this, can polarize the surface nicely. It pushes charges, so the charges, get my props. The two charges, it'll push the charges back and forth in the surface. Okay? So the polarization is substantial, and therefore the light undergoes a big change in the way it travels from in air where there's sort of nobody to polarize, the air is minimal, to the surface where, you get big polarization. And that causes a big reflection. So horizontally-ish polarized light bounces beautifully off of these surfaces at shallow angles. In contrast, vertically polarized light tries to push the charge up and down, in and out of the surface. Well, it can't go out of the surface. There's nothing there. It gets stuck. It gets blocked at the surface. So the polarization response of the surface to vertically polarized light is weak. So the light doesn't undergo as big a change from traveling in air where it doesn't get much response to traveling in the surface where it doesn't get much response either. There's not much reflection of that light. So this glare you're seeing there is preferentially horizontally polarized light. That's what reflects nicely. The vertically polarized light punches in and goes into the surface and goes and hits the wood and is absorbed. So this is mostly horizontally polarized light. And to show you that, these are like giant polarizing sunglasses. So when you go shopping for sunglasses, you can buy it by brand name and blah, blah, you can really look cool. Or you can go looking for where it says polarizing. And if you buy a polarizing sunglasses, even if they're Junko brand made in, made wherever. I won't go into trade wars here. Those polarizing sunglasses have a feature that they deliberately block horizontally polarized light, the prime component of glare. So, what I can't tell in advance is which of these I'm going to bring up first. The glare went away. If I rotate this guy, now this is sunglasses. Oh boy, this is hard to do. Okay, this is sunglasses on their side, where they are blocking not horizontally polarized light, but vertically polarized light. It makes the glare worse. So this is not how sunglasses are oriented. They're rotated. And there you can see the effect. As I rotate this filter, which dates back in concept to it was original to Edwin Land, the founder of Polaroid Corporation. He invented this. And it's a material that uses a chemical structure to block one polarization, depending on how you orient it. So it's now blocking horizontally polarized light. No glare. It's now blocking vertically polarized light. All glare. Is that okay? The effect is real. It's big. And this is the value of wearing polarizing sunglasses. They block horizontal polarization. And therefore, all the low angle light that skips off surfaces that are horizontal, which is the lake at your country house or whatever, the dashboard of the hood of your car, it's all horizontally polarized light, primarily. Block it, the glare goes away. And if you turn your head on your side, it comes back, because now you've spoiled the orientation of the sunglasses. Any questions about that? So even if you don't own or buy polarizing sunglasses, go play with them in the drugstore or whatever. Just you can just find a glary spot off the floor and do this, and you'll see it. It's a real effect. Okay? Sunlight. So that's my story of sunlight. Any questions about things you wonder about with sunlight? Hopefully I haven't said. Do you have polarizing sunglasses? No. Yeah. Yeah.
So sometimes when I wear polarized sunglasses and then look at my phone, it turns rainbow.
Yes.
Why does that happen?
Okay. Question is sometimes you look at your phone, it turns rainbow. It's because the technology that creates these flat screen displays involves polarization. They're sending light through a sandwich of a polarizer, chemicals, a second polarizer. And what the chemicals do is they either let the light go through without changing its polarization, or they rotate its polarization. So it is possible with chemicals to take the polarization of light and twist it. And those liquid crystals that are in the display, the so-called liquid crystal displays, they're able to rotate the light's polarization to change it from vertical to horizontal. And if you've got two polarizers, it depends on the technology exactly how they do it. If you've got two polarizers, do I have two? I've only got one. If you have two polarizers that are aligned the same way, the first one cuts out half the light because it takes away one of the polarizers. The second one does nothing because it's just there's nothing else to take out. But if you rotate that second one so that so this one kills off horizontally polarized light, and this one kills off vertically polarized light, it's black. You can't see through them at all. And if you do that, and then you put chemicals in between that can rotate the polarization, you can turn on the ability for light to travel through it by turning on that rotation. And then you do that electrically. So they use electric fields to orient the liquid crystals so that they allow the light to go through or they don't allow the light to go through, and everything in between. So that's how they're turning on and off pixels. Is that okay? So they're polarizing. The light that's coming out, at least used to be strongly polarized. It was the polarization that came through, and that would mean when you're wearing polarizing sunglasses, one way you'd see the screen, and the other way nothing. So that was too much. So in the general evolution of technology, the engineers wanted to make it so that it was sort of as simple as possible. So you didn't have to like take off your polarizing sunglasses. And so they hid that effect from you. And the way they hid that is after light comes out that last surface, they change it into a mixture of horizontally and vertically polarized light, what's called circularly polarized light. And you can't tell. It doesn't have vertical or horizontal polarization anymore. The electric field's doing this. And so you get it from any angle. So they hid this. But at certain angles, it probably fails to fully undo the universal scrambling. That's the story of those. So the displays and stuff, they're working hard with polarization in there. And that's why your polarizing glasses can see weird things. There are lots of things in life that create polarization, that preferentially have polarizations in them. The sky is like that. If you're wearing polarizing sunglasses and you look at different angles of the blue sky, you'll see different brightnesses, because that light that's being scattered off the little antennas up there, it's coming out preferentially perpendicular to the little antennas. So it ends up with some polarization to it. Same with light reflected off of things like glass that's under stress, such as the tempered windows of your car or cars around you. You probably all have noticed when you're wearing, if you do wear polarizing sunglasses and you look at the cars, some of their back windows, you'll see weird color patterns in them. You'll see the stress that was left in the tempered window in the process of making it tempered, because that affects polarization. All right? I'll call it a day at that point.